Hi, and welcome to my next video about building siren detector software using TensorFlow and Python. At previous video we made this siren detector and it somehow works. Now let's try to make it a bit better. In this video we will try to make it run faster and we will try to slightly improve the detection quality. I have more ideas about the detection quality, but this will be a separate video. Here we will mostly focus on making this detector faster and lighter. So, why I'm doing this and what is the problems right now? First of all, as you can see, the model size. It's almost 400 megabytes, and this is actually quite crazy for such tasks. And inference time. This means how long this detector runs for one part of the data. And as you maybe remember, we change our buffer with sound every 100 milliseconds. And as you can see, sometimes inference time is about 1 second. Yeah, it's less than 1 second, but it's quite slow. And this is on laptop. On the Raspberry Pi, the situation is even worse. Plus, this solution right now requires a lot of RAM, and it will only run over 4 gigabytes or even more. And if you will try to run this on 1 gigabyte Raspberry Pi, it will just not work. So let's go, let's try to make it faster. First of all, let's think about how much data we need, because right now we have a spectrogram like this, and I choose spectrogram with siren. So as you can see, siren sound looks like this, and you might notice that the siren that we trying to catch is actually much longer than our it's a sine wave, and period of that sine wave is much longer than our detection window. So first of all, we're trying to catch something slow. And because of that, I believe that we don't need that much data. We don't need um, we don't need this fast Fourier transform results to be so densely packed in time. So maybe we can cut it in half or maybe 4 times. And as you can see, we have much shorter figure here. And the siren is still, let's say, detectable. We can still see that something is here. And in my opinion, it's even more visible here than here. So it should work better. Next consideration is frequencies, because right now we have quite high cutoff frequency, and we see that our siren is mostly in the lower frequencies parts. Yeah, we have some harmonics, but we're interested mostly in this. So we can cut higher frequencies, and we can get much smaller image to analyze with our neural network. So you can compare the sizes here and here. It's about 8 times smaller. So with smaller image to analyze, we will obviously can analyze it faster. And maybe we need to adjust also our network a bit. So this is a visualization of old and new network. The differences are minor, but I reduced the number of layers, I reduced number of parameters, and as you can see, without without quantization, and we will came to this a bit later. Without quantization, we have almost 2,000 reduction in size. So we had almost 400 megabytes, and we got 127 kilobytes. Dramatic degrees, and obviously this smaller network will work much faster, and it will require less memory. So we can, yeah, we can reduce the network size, we can reduce number of parameters, and we can reduce the image that spectrogram that our network will analyze. Okay, but maybe we can do something even more. Yes, we can convert this network to the special format. Previously it called TensorFlow Lite, right now it's Lite RT. And this format is analyzed only for inference, only for the execution. So it don't have any features that we might need for model training, for some optimizations, tinkering, and so on and so on. So it's quite lightweight and analyzed only for execution. And much more interesting, this format have option for quantization. What does it mean? It means that previously we had float 32, we had 4 bytes for virtually for every number in the network, for elements of spectrograms, for network output, for activation and for weights in the network. And we can replace at least some values with just 1 byte, integer 8. This will give us also dramatic reduction in network size. Obviously, we cannot replace 4 bytes with 1 without penalties in network accuracy. But let's take a look what will happen. So why does it means? Why does it matter? It's matter because some CPUs, most of the CPUs that we can see in embedded systems, from microcontrollers to the Raspberry Pi, they have more optimized execution blocks for integer 8. So yes, they can process float. While they can process float 32, it will take much time for this, and it will take much more energy. So we can replace a float with int8, and we can save time and we can save energy. And obviously, model will be lighter in terms of memory size, just because we have less data to store. So how this works? How is it possible? Quite simple. Actually, we will just map numbers from the float scale to the int8. And obviously, we have much less numbers here than possibly numbers here. So sometimes numbers that quite close one to another will be scaled to one number. And in that case, we will lose some accuracy. We will lose ability to distinguish between them. But most of the time it works. It works okay. So yeah, we will lose some accuracy, but network will still work, and we will still get our detection result. After all, as you probably remember, in fact we need Boolean output. Is this siren or not? So int8 has much more than just one Boolean. But obviously, int8 inside the network instead of floats will decrease our accuracy. So let's try it. Let's say, how can we do this? How can we implement this? Actually, we didn't have to change our training logic, but we need to add some converter that will take the saved TensorFlow model, Keras model, and it will convert it to TensorFlow Lite model. And you will see code for this in my Codeberic repo. everything is already done, so you can check out the fresh repo and try it. Okay, we made model lighter, we made model faster, but we still have problem with false positives, just because initial dataset was quite small and it was recorded on the street. And on the street, you don't have, for example, vacuum cleaners, you don't have sonic toothbrushes, you don't have anything like that. And if you have a microphone in your house near to window, it will pick up the sirens, but at the same time, it will also pick up your house sounds. And you will get false positives for these house sounds just because model has no idea what is it and how to deal with it, and it can count that it's some weird kind of siren. So how can we counteract this? Record we can record some sounds inside the house, and you will see example commands in the README file in the Codebreak repo. So we can record normal sounds, non-siren, and we can use some of home tools to give the network some understanding that this is real life sounds, it's not siren, you should not trigger on this. Okay, and with anything this applied, let's take a look at the trained results. And maybe you may think this is old one, this is new one, and maybe you may think, oh, old one was better because look at the loss. It drops to almost zero or maybe to zero quite fast. And with new one, this loss is dropping quite slowly with the training. But actually, this picture is in practice, this picture is much better just because here we have a thing that called I forgot the term. Sorry, that called overfitting. Yeah, overfitting. This means that actually network remembers something, some pattern that was in the data and act on that pattern. It not generalize. Why does it bad? Anyway, we have almost zero loss, so why not? Maybe we can just leave it like there. Well, if it not generalize, it will act on that pattern. That means that when you have different microphone, different kind of sirens, so some new vehicles with new sirens, you have something changed in your system, and it will not be able to detect that this is a siren just because it's not generalizing, it just remembers. And here in the new network we have much better loss picture, so here we have some kind of generalization. And actually we can say that okay, right now it seems like it work. Actually it's not remembering it, it's generalizing, and that's good. So let's take a look at the inference time. Here we have old model run, and yeah, as you remember, it has quite huge size. And take a look at the inference times. Sometimes it's 0 0.4 of second, sometimes it's almost 1 second. And on the laptop that I used, when this model, on the laptop that I used, when this model ran, we had almost, not almost, we had 14.5 watts power usage. When at the same laptop, at the same microphone, we will run new model. First of all, and yes, this is a TensorFlow Lite model, so it's even faster. First of all, inference times, uh, 50 milliseconds, plus minus, dramatical decrease, as you can see. And TensorFlow Lite model is only about 14 kilobytes, and this means that we can try to fit it in the microcontroller. We maybe don't need a normal PC with Linux, and this will be the theme for some of my next videos. And as you can see, power usage significantly dropped. Yeah, it's not dropped to maybe 3 watts just because this laptop has almost 6 or 7 watts idle power consumption without anything running. So we cannot, with a normal laptop, we cannot go too low. But you can see that it's dramatical increase in the speed and dramatical decrease in the power consumption, and almost also in the memory consumption. So feel free to check my Codebird repo. You will find all required stuff there. You will find README and you will find updated code. Feel free to experiment with it and tell me what do you think. Thank you for watching. See you next time. Bye.